Good morning, ladies and gentlemen. This is our final day of the online training on HOMER software. In last 4 days, we have already covered most of the things in this software. Today, we are going to cover the large systems with multiple diesel generators, islanded utilities and large village systems, operating reserves, solar in large grids, and value of storage in multiple generator systems. Ladies and gentlemen, the content and material of this online training is already available on our website. You can go and download it from there. Since it's the last day, we would again request you that you may ask any questions and queries you have with the experts right now. But even if you have some queries later on, you can just send us the emails and we will address those with the experts. So with this, I may request Peter and Silver to carry on with their demonstration. Over to you, sir.
Okay, thank you. And this is gonna be similar to the previous days when I'm gonna let Silver do the most of the demonstration. But I do want to reinforce what Hassan said about we love the questions, and so feel free to ask the questions, and I really appreciate all of you. The great attendance that we've had. But for now, I'm just going to pass it over to Silver to jump right in.
Okay, thank you, Peter, and thank you, Hassan. So welcome everyone for today's session. It's the last day session, and we'll be focusing on the gensets. So combining multiple gensets, and also adding PV to gensets, and working with multiple gensets, and including the maintenance requirements for the gensets. So just like yesterday, we can work on a blank, we can start with an empty HOMER file, and we can set, let's say, again, a small village in Alaska. So we can say Alaska. So this is a system for a small cooperative utility in Alaska. And again, we can put in the location in Shivak and let HOMER look for that location. So in a similar manner, you can also do a project like in the Maldives with a very isolated system, and you can simulate a similar village like this one. So then we can, as previously done, we can just provide a genset back to a genset to the small village. To start with, we can input, if we have a file like what we have here, as the electrical demand or the load profile of that village. So this is an hourly data for a year, and we can let's say mark this as a year for 2011, which was taken. And you can see the load profile, the DMAP, and here at the bottom you can see the average energy per day, and the peak kilowatts, and the load factor. So with this load, we can just add an auto-size genset for a quick design, and we can use the default settings, but we can also put in the price of fuel to be 1.2 liters, just to have a reference. So this will be our base case, and if we do calculate, HOMER will look for the best capacity of genset, and with the results that we got, HOMER chose a 580
I lost audio.
Silver, you're not audible.
Silver, could you just check your microphone? We can't hear you.
Yeah. Hey, Silver. So Silver. Well, maybe I'll take over for him here.
Okay,
How can we
I'll
get
just
his
text.
attention?
Okay, I'll just quickly text him. Maybe he's not able to hear us.
Oh, shoot. I don't know which screen I'm showing.
Can you see the screen now, Peter?
Yes.
Well, we took it away from you because we couldn't hear you. So I'm not sure who has control right now.
Okay.
Peter, we have given back the right to Silver.
Okay, great.
All right. Okay. Can you see my screen now? All
Yes.
right.
Yes.
Okay,
But we didn't hear. There was a
just
couple of minutes there when we didn't hear anything.
Okay, so I'll just go through it again. So from our previous village, we can simulate what is already existing in that village. So in our previous model, we let Homer find the best capacity of a genset, and it chose 580 kilowatt. Now, for existing gensets in a village, we can simulate, in this case, this village has already a genset of 550 kilowatts, so we can say existing genset. Just to indicate that this genset is already there, and we can put here 550 because in this village they have already a 550 kilowatt genset. Now we can add other information. So based on that 550 kilowatt genset, the price is for capital cost is 0. 0 means it's already there, so you don't have a capital cost. But in case you want to replace, the replacement cost is 200,000. And based on the data available for operating that genset, they're spending around $4.5 on O&M per hour in operating that genset. This is over and above the cost of fuel. So for the fuel cost, it retained the $1.2 per liter that we already inputted. For sizing, since it's already there, we can put here the 550, but we would always have that 550. Sorry, I can't find the screen now. And removing the 0 means all the models of Homer will include this 550 kilowatt existing genset. So we can model this particular system with the existing genset and benchmark the parameters that we can use as the new baseline now with the existing genset. So we don't have a capital cost, but the net present cost is 13.8 million, mostly as a result of the O&M cost. And the energy is 42.9 cents per kilowatt hour. So this particular model is an existing system. And would it make sense to add a smaller genset? If we look into, let's say, the result and see the time series, we can see that there are parts in a year that the demand is smaller than the minimum capacity of the genset. In this case, we have not set yet at 30%. So we'll complete that parameter. So we go back to to our model genset. The more details we can provide on the genset, the more accurate we can simulate the system requirements or the actual performance. So we have here at the bottom the minimum load ratio. By default, it's 25, but in this case, we're setting it at 30. So that's the minimum capacity that the genset should ideally be running. And for the lifetime, so the default is 15, we set it to 60,000. Okay. So then we can also make more detailed fuel curve. Let's say this is a fuel curve, and based on the data that we got from the field, we can say at 275 kilowatts, the genset is consuming around 79.2 liters per hour. So that's one point. So that adjusts our fuel curve. And at a higher load of 550, that's almost its full load, its consumption goes up to 151.25 liters per hour. Okay, so this creates a fuel curve. I'm just checking if, and we can set the capacity at 550, right there. So with this capacity and existing data on the fuel curve, we can model the existing genset more accurately, and we can run this also in HOMER.
Silver, oh, well,
be,
when you get back to it, show the efficiency curve, because that's always interesting. But
okay,
go
right.
not right now.
You,
go
Peter.
get back to it. Yeah.
So we can, yeah, just to go back. So
okay.
we have this. Okay, we have this fuel curve because that's what we entered based on the information that we got. So that's a fuel curve. The vertical axis is the consumptions in liters per hour, and the horizontal axis is kilowatts loading on the genset. But if you click on the efficiency, you can see that the efficiency curve on the operating range of the genset is has a low variation, and as you can see, the efficiency suddenly drops below that minimum load requirement. So we wanted to operate the genset mostly on its high part of its efficiency. Okay, so just to show the fuel curve and the efficiency curves. So going back to our results, this will be our new baseline based on the existing data, and with the additional inputs that we provided, we can see now that the actual cost of energy is at 36.9 kilowatt hours, 36.9 cents per kilowatt hour. So this will be our new baseline. And as I mentioned earlier, if we look into the time series plot of the energy, because we raised the minimum load requirement from 25% to 30, there are a lot of times that the load is less than the minimum requirement of the genset. So in most cases, a dummy load or a saline solution is added to meet that minimum requirement. So this results to an excess energy. If you look into the electrical part, you can see that there's 3,125 kilowatt hours of excess electricity because of the nature of the genset and the load profile of this village. To make it more efficient, we can add a smaller genset, and we'll let HOMER look for the ideal genset that can run in when the load is lower than the minimum load requirement of the existing genset. Okay, so we can add a genset, and we can use medium-sized isochron genset. Then we can put here a new genset just to distinguish that we're putting in a new genset, and we can label also the abbreviation with new gen. So this is to distinguish the existing genset with the new genset that we're putting in. Now we can adopt a 600 kilowatt, $600 per kilowatt of capital cost, and the replacement cost is 450 with an O&M cost of $0.006 per hour of operation. And we'll let also a minimum load requirement of 30% similar to the previous genset, and also simulate a 60,000 hour lifetime of that genset. And let's allow HOMER to select if it doesn't need an additional genset, 100, 200, 300, up to 600 kilowatt of capacity, because we have a 550 kilowatt existing, and our peak is also around 500. Then just to be fair with the other genset, so we can copy the existing fuel efficiency curve. Take note of this intercept of 0.013 and 0.262 on a slope. So we can copy these values and put this in the new genset, just to have a similar fuel curve of a similar sized genset. So here we'll put in 0.131 and 0.262 on that slope. So this is another way of working on this curve by setting the intercept and also the slope. The other way we did was to put this actual rated output and fuel consumption. Efficiency should be similar with the previous one. Okay, so we also provided the HOMER to select from several sizes from 100 to 600 in increments of 100 kilowatt. Now we have this configuration here with the new genset, and we'll let HOMER check if it's ideal to add a genset and at what capacity will be needed. So as a result, HOMER provided 400 kilowatt genset as an ideal size, and it improves the cost of energy and also reduce the net present cost of that genset. Okay, so when we look into how that second genset would operate, we can look into the time series, and the default colors for the genset and the existing genset are the same, but we can change that. And let's say for the new genset, we'll put that below and use a darker color like red to distinguish this. And then we can zoom in, and let's say in that in one day, or we can look into June 15. We can notice that the red line is for the new genset. So when the load is low, a smaller genset running at higher loading will have a better fuel efficiency. So Homer would select a smaller genset to run during the time of the day when the load is low. But when the load picks up, it shifts the operation to the existing genset, which is a larger one, the 550. And when the load goes down, it goes back to the smaller genset. So with that operation, the additional genset actually reduced the fuel cost or fuel consumption. If we compare these two results, the existing genset actually reduces fuel from 715,000 to 160, and the additional fuel is passed on to the smaller genset. But the total fuel consumption is down by 15,000 liters. So there's an advantage of having a smaller genset. If we look into the overall list, Homer would also consider other smaller sizes like 300, 200, even as small as 100 kilowatt. But the fuel efficiency and also the passing of capacities when the load varies is not as efficient as the 400 kilowatt system. So in this configuration, Homer is providing us an idea that the ideal size for additional genset to reduce your fuel consumption would be a 400 kilowatt system. Okay, there could be questions at this point. So any question, Hassan, from the audience, from the participants?
Yes, we have few questions, but I think we can address it later on. They are more on the economic side.
Okay, all right, thank you. So yeah, Peter, do you have additional inputs, or we're good?
No, it looks good to me. It looks good.
Okay.
We see this frequently with generators running at oversized generators running at part load, and putting in a smaller generator can be really helpful.
We just got a question from Anand Kumar. Does Homer considers ramping capability of generation assets while designing microgrid?
Peter, you want to answer that? Ramp rate?
Sure, but it does it to the limit of the resolution of the analysis. So, if you're typically doing an hour-long time steps, you're not going to be able to model the ramp rates. And even at a 1 minute time step, it's true that the larger generators, the utility scale, coal-fired plants ramp slower. Would be in megawatts per minute, but your diesel generators don't. So, although you can model, gas turbines with Homer, the default resource are these reciprocating engines or liquid fueled generators, and their ramp rates are they can go from 0 to full load in less than a minute. So ramp rates are a bit much more of an issue when you're talking about large grids. So that's not something that gets typically modeled with Homer. I think we've got a lot of attendees here. I'm just noticing from the questions that we're getting, we've got a lot of attendees here who are really, experienced with, sort of typical large utility plants. And so Homer's really designed for the smaller distributed plants, where, if you've got a liquid fuel generator, it's the ramp rate is less than a minute.
Yeah.
But Peter, just I think just to clarify on this point, maybe the participants here is more on the aspect of this generator. Like for example, if you have a small distributed system, you have a PV installed with a genset, and the PV production is decreased somehow due to a cloud coming on top of it for 30-40 seconds. So the diesel genset would take a minute to put it up to that power. So how does Homer, I mean, go on with this setting?
Right. So if the diesel generator is off, if it's not operating, then you're right. It's not going to respond fast enough to handle a cloud coming over. So that's why these operating reserve constraints, which we've mentioned, yeah, and Silver's showing them right now. That's why these operating reserve constraints are so important, because they're forcing the system to have a generator that's operating. So you're right. If it's not operating, it's not going to respond fast enough. Even a diesel generator isn't going to respond fast enough if for a cloud going over a PV array. But if it's already operating, then it can. It can ramp fast enough to handle the drop in PV output from a cloud passing over. If it's already operating at part load and it's just a matter of ramping it up from part load to full load, the diesel generator is very fast at that. And so that's not a problem. So that's why this operating constraint restraints are requiring the system to have enough resources actually operating to handle that situation.
So does that mean that in that case the genset wouldn't have decreased amount of working hours even if we have a PV installed with it?
So if all you have is PV and no storage, that's absolutely right. You're not
Okay.
going to reduce your runtime on the diesel. And that's
Hmm.
why those are low penetration systems. They're often called fuel saver systems. They're simple. They don't require batteries, but they're very limited in the savings that you get because one, you're not getting any O&M savings because you're not reducing your run hours. And two, the solar, it is saving fuel, but it's forcing the generator to operate at a lower level, less efficient level. So it's not saving as much fuel as it would if you could turn off the generator. So
Yeah.
those
We'll
low
cover that in
penetration.
the next exercises.
Oh, great.
Yeah.
Perfect segue to the next section. Thank you, Silver.
So thank you, Peter. So as Peter mentioned, it's important for us to have that operating reserve. So it can be in this case a 10% on the load. So there's a 10% reserve, and we can also put in uh, a reserve on the peak load. So in our case, we added 100 kilowatts over that reserve. So this can be equivalent to, let's say, 19.25% of the peak. So in some grid codes, you also do require that peak reserve requirement to comply for reliability. So if we add a peak load requirement for our system and simulate, we can see that Homer will still utilize the existing systems, but you don't see the smaller the 550 anymore because it will require an additional capacity because of the peak load that the additional reserve that we required. So if we look into how the system operates, we have here the existing one, and we'll have another color for the new one. And there you can see that that several times the genset will turn on just to meet the extra capacity that we need for the reserve. So that's the impact of having a increased requirement for reliability by adding a reserve requirement. So if you look into the June, in our exercise, we have a June 15 date sample day. Okay, sorry. All right, so we can see here that two generators operate most of the time, or they exchange capacities more often because of our reserve requirement. So this is the impact of having a higher capacity requirement. So moving on, going towards other options of improving the system. What if we add solar in the system? Okay, so we can add solar as we have discussed yesterday. In this time, we can simply use a flat plate system, but we'll use an AC system so that it's easy to incorporate into our next system. Okay, so and we can use the default parameters, but again, the software will be looking for the solar radiation data, so we can download data from the internet. We have two choices, NREL and NASA. In this case, we'll just use NREL data. Okay, and simulate the system. So adding PV, we also allowed the HOMER to look for the best capacity for the PV to work with the two gensets. So HOMER recommended the 288 kilowatt peak, but as you can see here, there's a warning sign. As Hassan mentioned about the question on the stability of the system in terms of fluctuating cloud cover and the genset dropping up and down, HOMER is recommending to use storage like flywheel or battery bank to smoothen that transition. So in this case, this just a fuel saver configuration, and we can compare that the fuel actually reduced, and now we have a 9.25% penetration in terms of the solar. Okay. Any questions on this system, Hassan?
Yes, Silver, we have a question from Faizan. Can you elaborate the CC and LF in dispatch column?
Okay. We will have a better appreciation of this CC if we have the battery. But in this case, if you look into the overall list, the CC and LF, or the load following and cycle charging results are almost similar. So in terms of mechanism, if you're using CC, if you have a battery, it tries to fully charge that battery and stop the genset, but the load following will just follow the load instead of cycling the battery. So in our example, because we don't have a battery, the performance of the LF and the CC dispatch strategies are the same because there's no difference in charging the battery, which is not included in our system. So we'll have that explanation if we have the battery in the system.
Okay.
Okay,
We have
so
another question. Okay.
yes.
Should I go on? Okay. So can you simulate a case with the solar, genset, wind/utility if you can, as an example?
Yes, we can. We just add the wind turbine, but in this case, we're just adding a PV. So I just wanted to emphasize the stability because it will have a similar impact on having the wind. It's an issue of stability. Again, we go back to the project and constraint. So let's say we've mentioned about the peak requirement on the system, but what if we require a different level of reserve as a constraint for the solar? As Peter mentioned yesterday, you can derate the capacity of the solar based on the stability, but in this case we can use sensitivities. So let's say we put here 25%, 75%, and 100%. That means we have to have reserve of this percentage when we're dealing with solar. So what will happen is HOMER will look for the alternative reserve from the genset to meet that requirement, and it will change how the system would size based on that reserve requirement. So we can simulate, and with the sensitivities that we have, HOMER will look into what will be the configuration of the system if we have these three levels of reserve requirement. We can use the graph and okay. It's not showing yet because we only have one parameters. So here we just go into this table. So just notice that if we have 100% requirement for the solar reserve, notice that from our existing 550 kilowatt system, solar HOMER is recommending only 243 kilowatts of solar because the existing gensets that we provided can only cover 100% of a 245 PV system. But if the reserve requirement is lesser, let's say 25%, then the system can accommodate a larger PV system because of our requirement of a lesser reserve. And then if you have like 75% requirement, similarly, the system can only accommodate 284 kilowatts of PV because of that reserve requirement. So depending on the reserve requirement for reliability, HOMER will adjust the capacity of the PV as a variable resource to meet that reserve requirement. So if we add wind to the system, it will be a similar case. So we have here for solar, and we can also put here these constraints for wind, depending on how reliable we want the system to be and what cost can we afford to meet that reserve requirement. So Hassan, any further question on that issue?
No, we don't have any questions until now. We would again ask the
Okay.
participants to just ask any questions if they have from the experts. But the floor is open to ask any questions. Go ahead, Sunil.
All right. So we have shown how the reserve requirement would affect uh, the operation of our the configuration of our system. Looking at the next. Okay, there
Silver,
was a question on. Yes.
yes, yes, we had a question somehow kind of a discussion. I mean, one of the participants had a question that once you are designing the system, it has been seen in the software that if you put up a very big battery bank in the system, and it is also attached to the utilities, so somehow the software uh, considers the battery bank to be some kind of a grid state and considers grid down. Have you ever encountered this kind of situation while designing systems with very big battery banks?
I'm sorry, I missed a key word there. The system considers the grid to be a very big, what was it you said?
They were saying that once designing the systems, if the battery bank is too big, so the software somehow was uh, considering battery bank to be the kind of a grid feed in, while the genset was having some trouble with integrating with that battery bank. It was considering as a grid or something like that. He was just a kind of a question. I don't think he was very clear on that one.
Well, the only problem with a battery bank that's too big is that it's too expensive. But you know, the bigger the, assuming it's got a reasonable control system, the bigger the battery, the better for the grid. It just might not be cost effective to put a big battery in.
And just to add up on that question, could we have a possibility to compare two battery banks during the simulation? Like, for example, we have been going on with a lot of talks on lead acid versus the lithium ion. One, on the other hand, is a low cost, while the other one has a big life cycle. So, does the software has any provision to compare both of them?
Yes, yeah, you can put two battery banks into Homer. It's a little different. You just in actually, uh, um, Silver, you want to show the controller, and go open up the controller, because the properties of the controller, and then go to click on one of the two. It doesn't matter which one. Up above. No, well, okay, there. Click on that. Did you click on one of those?
I think
Which
There
one
we
would
go.
you like to open?
Yeah, no, that's good. That's what I wanted. That screen right there. So you can see it lists the capabilities
Okay.
of
All
the
right.
controller, and it shows you can have up to 20 generators. You can have 10 battery banks, 10 PV arrays, 2 wind turbines, etc. But there is one difference here. With the PV array and the generator and the wind turbines, Homer will simulate systems with up to 20 generators, and I think we're later in the today we're going to show the dispatch strategy for multiple generator systems. So with storage, it's a little different. You can have up to 10 battery banks. You probably would never want to do that, but what you suggested actually is a very common thing that people want to model, with comparing lead acid, inexpensive lead acid batteries that aren't very durable with more expensive lithium batteries that are much more durable. You can put both of them in the model. Unlike PV and generator and wind turbine, though, Homer's only going to simulate one battery bank at a time. So it will do what you just said, which is you'll have results for the lead battery and you'll have results for the lithium battery, and you can compare them and compete them and see which is better. But Homer can't model a system with both types of batteries in that system, but it can compete them against each other, compare them, in a single model run, but not in an optimization, but not in a single simulation. I hope that was clear.
Okay. So we have a participant who would like to ask the question directly from you. So we would unmute Muhammad Ali Qureshi, and Qureshi, you can ask the question now.
Yes, thank you so much, Mr. Ehsan, for letting me ask the question directly. Actually, my question is related to that when we are sizing the batteries, for any particular system, normally it has been observed that in order to optimize the system, the Homer actually, I mean, when it does do the simulation, it gives, a very good, big battery sizes. It recommends a very big battery sizes just to optimize the system. But in actual scenario, if you use such a big battery sizes, normally the batteries they start acting as in a grid forming function, right? So is there any way through which we can restrict the size of the batteries and also optimize in a way that the batteries do act in a grid following mode rather than grid forming mode?
So anytime the system is running with the diesel off, the battery will be the grid. You need a grid forming inverter. If you don't have a grid forming inverter, you can never turn the diesel off, or or you can never run. Or if you're grid connected, you won't be able to run if the grid is down. So there's two pieces to your question. One is Homer kind of assumes that you have a grid forming inverter if you want to run diesel off. So that's, and then you also asked about restricting the size of the yes, it's very easy to restrict the size. In this, using the search space, you can put in whatever sizes you want. If you're using the optimizer under the advanced tab, there's an upper limit, and you can just say that's the maximum size that you want. So there was really two different questions there, and they seemed like separate questions to me. I hope I understood the question correctly.
Yes, I think the first part is very clear that while designing the batteries, you have the provision to limit the capacity which is available in the software. And the other part of the question was about the grid forming function. And you have mentioned that the system basically requires it to have a grid forming function in terms of a battery to go on with it. Am I right, Peter?
If you want to model an off-grid system, you have to have a grid forming battery. I mean, if you want to, excuse me, I didn't say that correctly. If you want to model a system that runs without a diesel generator or a grid, you have to have a grid forming inverter. Absolutely. They're a little more expensive, but yes, you have to have a grid forming inverter. Otherwise you can never turn the generator off, or run with the grid down.
Yes. Do we have any other questions? Okay, one of the question asked, okay, so Qureshi says, thank you very much. I think the answer is sufficient. He's already okay with it. So we have another question from on the aspect of economics. Peter, there was a question that one of the participant was asking that the calculations are basically the economics is given on in terms of dollars, but you have the provision to change the currency. So they said that once you change the currency to our local currency, whatever it is, the results somehow do not match. Have you encountered this kind of an issue?
Well, you can use any currency you want, but here's the you have to be careful, because if you switch to a different currency, you have to make sure everything is in that currency. So it's easy to make a mistake there, switch to a different currency, but you have to absolutely make sure that you've changed all of the numbers. You have to check every component including up here in the economics, where if you have the system fixed capital costs, system fixed O&M costs, those have to change as well. So yeah, you can use any currency you want, but you have to, but you can't use two currencies in the same model. So totally fine to change the currency. I just have to check that you're consistent throughout the software with the new currency.
And just for the information of participant, can you show from where you can change the rates of the currency?
Okay. Yeah, so we can go to projects on the top. Then you can go to the economics, and you can see here currency. So I would recommend to start using changing the currency on the onset of the project, so that everything will be under one currency. And the default prices of the items in the library are in US dollars. So be careful of using the default values if you're using a different currency. You can easily change the value of that item differently with a different currency.
Silver, just show, change the currency just to show that the symbol changes.
Okay,
it doesn't
so
matter which one, just pick something.
Yeah, just to maybe, okay.
Let's change it to Philippines currency. Where?
Yeah,
Okay.
just pick
So that's
something.
a peso. Okay, that's a peso currency, all right?
Yeah.
So you can see that the pesos here, the currency here has changed. And if you look into the gensets, you have these symbols also changed,
But
just to be consistent on all. Yeah.
It didn't.
But the numbers are the same.
But the numbers are the same.
Okay,
right?
it did not convert the values into Philippine currency with the exchange rate. It did not.
Yeah.
It just changed the symbols. That's why when you start modeling, you should start setting the currency right according to your requirement, and maybe have an Excel file of all the components priced on a single currency converted to that single currency. So from US dollars or euro, you can have it in Philippine peso or Indian rupee or Indonesian rupee.
Yeah, so you're not
just to be consistent on your.
It's not going to actually change the numbers because exchange rates change all the time. That would be, I don't know how we do that. So yeah. So you have to like Silver says, you have to be really careful to check all the default prices. You need to manually change them.
So basically, it just changes the symbol of the currency. Otherwise, the numbers remain same in terms of.
Right, exactly.
Yes, correct.
What we thought was that if we change the currency and gave the equivalent changing rate, it will immediately convert all the numbers into the currency conversion rate. But I guess that's something else.
No, we don't have a way to put that rate in.
Okay.
No.
Yeah. So that's the.
I think it's okay.
That's for the currency.
Do you have anything else to say? We have another question.
What's the next question? Is it related to our model or another? Yeah, okay.
Yes, it's somehow related to the same economics. How does HOMER calculates the real discount rate?
The real it doesn't calculate the real discount rate. That's an input. But it converts that to a nominal rate based on the inflation. You know, if you go to well, there's a good article in the help file about it. But there's a simple formula to take the nominal rate and the inflation rate and come up with the discount rate. It's probably.
Where's that, Peter?
Well,
is it in the?
Here, let me open HOMER Pro. So yeah, no, it's under discount rate, I think.
Yeah, here's the formula.
Yeah, there you go.
Yeah, so you have inputs here. So here's the real discount rate, then the nominal rate, which you could borrow money, so mostly the interest rate, and the expected inflation rate. So it's like even off that inflation and interest rate in one to have that real discount rate. Is that correct, Peter?
Yeah, I mean, this is, you know, economics and math that, right. That's how you get from a nominal rate to in a real rate. You have to incorporate the inflation rate, and it's, you know, to a first approximation, the real rate is just the nominal rate minus the inflation rate. That's not exactly right. This formula is more accurate.
Okay.
We have a question from Stephen from Germany. I have got a question regarding battery storage. Is it possible to account for variable O&M costs that are dependent on the throughput?
Throughput. We'll try to. You want to answer that, Peter, or we proceed with the model that we can have the battery included in the system, so we can also touch on the throughput issue?
Well, the throughput is what determines the lifetime of the battery. So, so it's incorporated into the economics because through the replacement cost. So I'm not sure about. I mean, so that has a big impact. I think that is the impact of the throughput. Hopefully, that's adequate. I'm not familiar with any other costs besides the replacement cost that's a function of throughput.
Yeah.
Stephen, if the reply is sufficient, it's okay. Otherwise, you can just clarify your question more. So we are over with these questions, so you can carry on.
Okay. So maybe we can help answer those questions by proceeding on the next model of adding storage to the system. What if we add storage instead of capacity? Because storage can absorb excess generation and also fill in the gaps for the system. So we can go back to our configuration and we can add storage. So let's say we'll use a lithium battery and we'll just use the default numbers, but we'll have a search space, okay, of a maximum of an upper limit of 1,000 kilowatt hour or a megawatt of battery in this system. So we can also change this string into a 48-volt system, but it will check more on the energy content of the battery. So it's complaining now that we need to add a converter into the system to couple that battery into the AC bus. So we can add a converter component and we'll use the large free converter. Okay, so using a large free converter literally can take advantage of the energy storage system that has already built-in AC connection as charger and inverter. So the coupling is straightforward, and the cost is mostly covered by the battery that already includes the converter in its price. Okay, so if we look into simulating this system, how would HOMER consider battery in sizing also the PV system. We have still the constraints on the reserve capacities. So it will take us some time to complete, but we can look into why what will be effect of the battery in terms of filling in the reserve requirement of the PV, as we have set it into 3 different sensitivity inputs. Okay. So here we have, if we have 100% coverage on the PV, we have here different configurations. So it's selecting 280 pieces of 1 kilowatt hour lithium, so roughly 280 kilowatt hours. And if the reserve requirement is only 25%, you can see that more PV is accommodated, but the battery is also larger to compensate for that system. And you can see that instead of having a large second genset, as we have seen before, now it's selecting a smaller genset, because then the battery can supplement that system. And since we have specified that every time we run the system, we have to include the big inverter, like the original genset, all components, all the simulation will include that genset. So that means that genset will always be connected to the system. So in this case, there's no totally renewable energy system in our configuration. We can do that by reconfiguring the genset. So instead of having 550 only, we can have an option. What if we allow the system to not use any genset, just like the second genset that we have, we put here 0, just to explore what if we want to have a system that's purely running on renewables. Okay, we're deviating a bit on our configuration, but I want to emphasize the 0 point here on the sizing, so that we will have a choice of not using any genset and what will be its impact to a standalone system, because we already have the battery, as is earlier raised on a question, as a grid forming device that our ACPV system can ride on. So this also gives us an option for zeroing our fuel cost, but look into the capacity requirement of the system. So it may require a lot of capacity if we have a large requirement on reserve, especially on the solar. Okay, so this will be the last exercise before we go into multiple gensets. Okay, so bear in mind that we have, if we have 100% requirement, because of that requirement, there is no system here that runs totally on solar because of the 100% requirement on the reserve. That means you cannot really use solar alone. But if we only require 25%, then it still have required capacity, because having a large system will not be economically viable. So here, the reserve requirement is really a determining factor for sizing the renewable variable sources, and also the capacities of the gensets that will support that reserve requirement. Okay.
You know, Silver, there's a handy thing that it might be worth showing. If you click on the the upper left legend where it says solar reserve, just click on that once. The heading, column heading,
Which,
over on the far left, where it says solar reserve. Yeah, right. No, just a little further to the left, right there. Just click there. So it sorted it,
okay,
and then
yeah,
it just makes it easier to read, and you can see that the sizes of the PV is, monotonic. And then that little symbol, that little filter symbol is kind of handy too. You can filter so you can, so that's just a little handy thing that's worth showing.
yeah. So it helps us look into the results, especially if there's a lot of options. Okay, and you can actually export these values to an Excel file if you want to really sort it separately, especially if you're looking into the overall configurations. Because you may look for a specific net present cost or initial capital. So Homer will look into mostly on uh, uh, the default will be sorting it according to the lowest net present cost and cost of energy. But if you have a different parameter to look at, like say initial capital, then Homer can sort it from the cheapest system that you can start with to the most expensive one. Okay, so that's it for hybridizing diesel with solar and battery. So any questions before we move into
Yes.
multiple diesels?
Yes,
Yes.
Silver, I would like to emphasize on this point which you have just mentioned. This is a very important thing. I mean, you click on any option and the results will be sorted out according to that thing. I mean, this is a very important. I think you should just say it again for the information of the participant. I didn't know about this one.
Yeah, so Homer provides you this list of possible configuration. In this case, in the lower part, because we are using sensitivities here. So if we select the 25% sensitivity, then you have these architectures below. And this is based on categorized system. But if you click on the overall, it will give you the full list of different configuration. So depending on what's your target, you may be constrained with the initial capital. So you can sort here the systems that may fit your capital cost budget, but also look into what would be the equivalent cost of energy of choosing that system. So you can rank it based on initial cost, or the regulatory office would look into what would be the lowest cost of energy, what will be the architecture of that specific system, which is what Homer would initially use for ranking. So those combinations of sorting can be helpful if you want to look into what possible configurations you can use in a system.
Yes.
Okay.
So could you just stay on the same sheet? We have a similar question from one of the participants. What are the warning signs it is showing on left for this simulation?
Okay. So as I mentioned earlier, maybe we can go down here. So whenever you have here, if we read this system has a renewable energy penetration high enough to cause stability problems that require more detailed modeling. So with high variable renewable coming into the system, there could be stability issues with the system. So a battery can help that address, but the control mechanism should also be considered. So Homer will give you an overview of the capacity, but gives you a warning that you should also consider um, addressing the issue on stability if you're using variable renewables in this configuration. Peter, would you like to emphasize on this warning sign?
Sure. And this goes to especially to systems without batteries. That really limits the penetration level that you can have. And it also, or systems with very small batteries. You know, if you have a large enough battery, that can provide the stability. So, you know, we added that warning many years ago when these fuel saver systems, you know, without any, before lithium batteries came along, developers really didn't like lead acid batteries because they're not durable. And so there was a lot of interest in adding renewables to a diesel system in this fuel saver mode. But you have to be really careful how you can't put a whole lot of renewables. You know, if you go to so that warning is a pretty static thing, to be honest. That I'm trying to remember where we set it. Hold on a second.
Peter, we have another question from the participants. They are saying that in terms of the sensitivity results, you can see that the battery bank is about 336 kilowatt hours. This is a huge battery bank, and does the system, I mean, recommends any other option other than using this whole huge amount of battery bank, which would definitely be unfeasible to install for such a system?
Well, I don't know. People are putting in 300 kilowatt battery banks. So
yeah, these are container size battery banks. Yeah.
Yeah. People are putting in, you know, multi-megawatt battery banks. If Silver, if you click on overall though, you overall, you know, overall in the right, you can look at and say, okay, well, 336, we can't do that. But you can see there's many different sizes there. You could say, okay, well, let me look at one of these. Whoops, no, don't do that.
Yeah, so it can be as high as 5 megawatt
yeah,
battery, but
well,
that would be practical. So
no,
you
go
can
back to,
scroll down and which one?
yeah. No, go back
Maybe from
and sort by net present cost. Yeah.
okay.
So anyway, you don't have to use just because Homer says it's the least cost system. You can see there's a whole lot of systems here that, yeah, they're maybe a little more expensive, but not much.
Yeah, so instead of using 336, you can go down smaller
Yeah.
system, maybe a little over 200.
Yeah.
But your cost of energy will not really change that much. So
But
at least you know the range of
So
capacity you can play with.
can we just check, does it sort out the battery bank capacity? I mean, I would like to see what is
Yes.
the minimum amount of battery it's proposed.
well,
Okay.
it
So
modeled some really large battery banks, but it's not suggesting that you do that. It just just
yeah,
modeled them.
it's telling you that it's possible to use that, but it may not be practical in your case. Yeah.
And it's not cost effective either. But
Yes.
you know, it had to model it to determine that.
And Peter,
Yeah.
just for the clarification, so these warning signs, do they mean that the system is not foolproof? It is not recommending the user to go for this system. I mean, you were saying that you should include batteries or maybe increase the battery bank. So these warning signs are a sign means that this option is not recommended to the user, right?
Well, here Actually, if I share my screen, or no, Silver, if you just go to project optimization, project, the project optimization screen. Whoa. Oh, okay. I'll show my screen. Hold on. Gotta pick the right screen. So here I've gone to project optimization, and the warning is just generated by these values that you put in here. So there's nothing magic about it. This actually was ABB that asked us to put this in here. So it's saying that, well, Homer's not modeling transient stability. That takes a power engineering model that operating at sort of the 1 second level, and it's not gonna do the economics over a whole year. It's just gonna there's specialized software, and it's not Homer, other kind of software for looking at transient stability. And so if you're trying to push the limit on how much renewables you can put in with either a very small battery or no battery, you really do need to use one of these power engineering models that looks at transient stability. It's a totally different kind of model. Doesn't consider economics at all. It's just modeling the event. What happens if a generator goes offline really suddenly? The frequency is going to drop. You have a stability issue, and to a lesser extent, you can have the same problem. Like we've been talking about, if a cloud passes over too quickly, and you don't have any way to pick up that load. So if you have really large renewable penetration, you really need to look at you need to look at this transient stability issue. So Homer's an economic model. It doesn't do everything. And so we just put this warning in here, and it's based on those parameters. And maybe if you did some power engineering modeling, you'd say, oh, well, we could adjust these parameters right here. Issue a warning if an off-grid system has a maximum renewable penetration greater than 55% with a battery autonomy of less than 2 hours based on the average load. So there's a bunch of really technical stuff that we've put in this on this page. The most important one is this minutes per time step. This is where you set the time step. And so that's where that's at. And so we're not saying you can't do it. We're saying Homer's not the right model for talking about the actual feasibility of that. It says Homer could say, well, if it's feasible, it might be very economic, but you need to check the feasibility.
Okay. We have a follow-up question from the same expert, from same participant. For the most optimized system in your analysis, can you show the percentage usage of these batteries?
Can we show the percentage usage?
Yes, like the analysis which Silver just did. So
yeah.
Okay.
Let's pass it back to Silver, because if you pull up the here, let me pass it back to Silver. If you go into the simulation results and look at the battery operation, yeah, just click on any one of those, or double click on any one of those, and then look at the battery tab. There's a lot of information about how the battery is being used. Well, and also, what's the annual throughput? What's the expected lifetime? I think that's what he was looking for. Is that right? That's what you're looking for?
I think overall he was mentioning that during the working of this whole system, how much time is battery being used to feed the load? If I am right, I don't know. I don't think he meant by that.
I guess it's not showing hours. It's showing is showing in terms of kilowatt. Well, so because a lot of times the battery is supplementing the PV or supplementing the diesel. It's not carrying the load all by itself. You know, the time series plot, or have we showed that you can export the whole time series data?
I think it's possible, but we have not shown that. So you want to see that
Well, you know, yeah. So
export?
show them the table, and then you can just export. No, right where you were. Right where you were.
Wait a minute. I think the table mentioned above on the quantity, there is this tab energy in. So 21 megawatt hours of energy would be given by the battery, if I'm right.
So,
This one.
well,
Here.
yeah, right, yeah. That's showing the energy in and out. You can see the losses. It's not in terms of. I don't know how to do it in terms of hours because I don't know how to distinguish between if the battery's exporting power, but it's not, it's supplementing something else. I'm not sure how we would count that. But I wanted to show the table because you can export all of the hourly information to Excel, and you could do in Excel many things like count the number of hours, not just the kilowatt hours, but the actual hours that the battery is exporting or discharging power at different levels, you know. Right. So somewhere one of these columns is the discharge. There it is. So over here, generic. Where is it? Well, it's one of these columns is the
Here.
discharge power. That's
Yeah,
it's
the
the next
right
one.
Charge, discharge.
Go four over. So the next one over. Next one over.
Yes.
So if you put this into Excel and you counted the non-zero rows in then that would probably do what you're looking for.
Yeah. You can count the number of hours, non-zero values.
I'm not sure why though.
On that column.
Not sure why you do that, but who knows? It might be useful. Anyway, I think it's useful to know that you can export. You can look at the table like this. It's a bit overwhelming, but you can export it to Excel and do all kinds of stuff in Excel with all this hourly data.
Okay, I guess we have another question which is from Nadhira Primadasa from Sri Lanka. Can we add super capacitors as a component?
Oh, could you repeat that question?
Can we add super capacitors as a component?
Yeah, I think it's in our library. If you go to storage, it's in the big library. We have a supercapacitor. They don't they lots of power but not much energy. But they're getting better all the time. What's happening here? Oh. So if you pull up the storage tab, you can show that. What are you doing? Silver, go pull up a storage. Click on the battery. Silver. Silver. What? Silver, we might have lost audio.
If I think Silver Mic is turned off. Silver, can you hear us?
Well, Hassan, if you give me the
Okay.
the
Okay.
um,
We are transferring in the right side. Okay. It's over to you.
right, let me get the right one. So I wanted to show. Well, I just wanted to show here in this catalog. It's a pretty large catalog. Somewhere in here is a supercapacitor. I think.
So, Peter, since we are here, you can show the filter options.
Oh yeah, we could sort, we could filter. Yeah, that's true. But anyway, here's the supercapacitor. But if you look at the component at the parameters, you know, it doesn't it's good for a few seconds. You know,
Yeah.
this one put out 6.6 kilowatts, but only, I don't know what that is. That's like a 3.75 watt hours. You know, this I have to do the math, but that's like a few seconds. So it's not really practical, but I shouldn't say that. It's not. It can be really useful for the system stability issue, and they're getting better. Who knows? There might be new ones that are even better. Anyway, I did
They're
want to
more
show.
used on fast response supply.
What's that?
Yes.
They are used more for a fast response supply
Yeah,
because some chemistries would take some time to deliver a current immediately.
Yeah.
So
they're very fast
it's like a
response.
short burst of system
So
of current.
But Silver, let's get on to the multi-generator. I want to show the
Okay.
generator order dispatch.
All right. So we'll continue on, and we want to model a purely a multiple genset system. So we'll remove first the components. So okay. And we'll use a similar gensets of 3 kilowatts, 300 kilowatts. So what we can do is we'll first also clear the sensitivity. So we'll set this to anyway, we'll not be using solar, but we can just clear the optimization, the reserve requirement. Okay, so we'll add a genset,
And generator,
and
don't
we'll use.
Silver, put a small and a large one in. Let's put two different sizes in.
Okay, so what would you recommend, Peter?
So the 500 and the 1 megawatt.
These
Where
are
were we? Right
fixed
there. Right there.
systems.
Yeah, those two. The two at the top there. Yeah.
Okay. We'll use the default values and the 500 kilowatt, right?
Yeah.
Okay.
Right.
But these are too big probably for our load.
Well, we can make the load bigger.
Okay. We'll double the.
Well,
we'll
no, it's
scale this
okay.
up, or will.
Well, no,
Okay.
it's okay for because it's over 500 kilowatt peak, and then you need your operating reserve. So I just
maybe I'll just go through my to the materials that I prepared. So
okay,
we will
okay,
have
do that.
Okay. Yeah. So we'll use three similar gensets just to have an idea of how would Homer dispatch multiple gensets. So we'll use here let's remove this and look into assign your own medium genset, and we'll use a 300 kilowatt genset. Okay, we'll just use that default number. And we can put here 0 and 300 for the selection. Okay, and we can copy this to the library so it's easy for us to add this to our system. So like replicating this, and here, so we can use this genset, and but what we'll do is we'll name the three gensets separately. So let's name this genset A, but these are all 300 kilowatt gensets. Okay. And we'll also name them just to distinguish every genset from each other. And if we run the system and let Homer determine if how many gensets will it need. So Homer would play with 2 gensets at a time, and it also provides a configuration of the 3 gensets as a system with 3 gensets. So obviously, if we look into a typical configuration with 2 gensets, the 2 gensets would be working complementing each other, as we have seen on our other previous example. So if we change the color to red for the second genset and zoom in, so we know that the load is more than 300 kilowatts, so it will need that second genset to supplement the first one. So that's the typical operation of the 2 genset configuration in our selection. But Homer still included the system with with a third genset. So we would wonder why would what will be the operation of the third genset. In terms of fuel, we can check, or running time also. Genset A is running most of the time, and it's being complemented by genset B, as you can see on the D map. But genset C, you can see it only operates very few times. So it still needed that, but since it's underutilized, Homer ranks it as the most expensive system. So that's how it configures the 3 gensets. But we have, before we go to the dispatch strategy, just to be realistic about modeling the gensets, we can include maintenance routines for maintaining the gensets. So we can include here maintenance. So there could be 2 sets of maintenance on the gensets. One is every 500 hours. So let's consider maintenance. And first we would say 500-hour maintenance. So every 500 hours, the system is stopped for let's say an interval of 8 hours. Okay, we'll use instead of calendar, it will be operating time, and we can just leave the other parameters as is. Okay, but there's a second set of maintenance every 2000 hour maintenance. Usually this could be an overhaul type of maintenance. So here we can set 2000 and operating type of maintenance based on the operating time. And in this case, it's a longer period of maintenance covering around 24 hours. It's a full day. And just to distinguish it from the 500 hours, we'll just use $1 for the cost. So it will not affect our economics. But we'll be focusing more on how HOMER would consider maintenance in dispatching the gensets. So we have that for genset A. What we can do is also replicate that for the other genset. One thing we can do is we can copy to the library, and we can delete this one and copy genset A with the new parameter. So we can remove that, also remove B, but we can add our genset A and another genset A, but we'll rename that as B and C. So this will be genset B, so that there will be similar gensets, and this will be genset C. Okay, so all of them have those maintenance schedules already, as we have put that in the library, and this will be similar gensets with similar maintenance requirement. If we calculate now, what will be the, sorry. So the capacities did not, I may have missed something here. So due to capacity shortage, we look into, we may have not reset the capacity shortage requirement. Okay, we'll remove this and retain the system. So if we simulate the system, we'll have the system only with the 3 gensets altogether. If we consider the maintenance routine, so this simply shows that the system cannot operate without a spare genset if we have to consider the maintenance requirements, especially the 500 and the 2000 hour maintenance requirement. Okay, so instead of just running on 2 genset, there's usually a 3rd genset if you have to consider maintenance. All right, so Peter, you want to mention something about the
Yeah,
generator order?
Yes.
Okay.
And I've set up a little model to show that, so I can take back the control, I guess.
Okay, so we'll refer to Peter's model regarding genset control. So Hassan, can you
Oh
pass
yeah, here we
the
are.
control
Thank
to?
you.
Is it?
Okay.
Is it?
Okay, so I just set up a little model here. I used a commercial load. I put in PV and battery, and I have 2 generators. And we recommend this if you're with 2 generators. It might not be essential if you wanted to model a system with 4 or 5 or 10 generators. It will run much faster if you use the this generator or dispatch. I think I might have lost control. Did I lose control?
I think.
Can you see my screen?
Yeah, Peter. Yeah, we can see your screen.
Okay. All of a sudden it looked like it changed. So this is so what I've done is over here on the controller, I removed the defaults. The defaults were the cycle charge and load following, and I'm using this generator order here. And so this is more similar to the way that I think a lot of utility operators work, where they have defined limits. They say if the load is between these load levels, we'll use this generator, and then as soon as the load reaches some level, we turn on a larger generator. And so and they have this merit order of dispatching or committing different generators as the load increases. So so we have 2 generators here, a 5 kilowatt and a 1 megawatt generator. And what Homer will do if you're using the generator order dispatch strategy is it will just work its way down this table, and we could add more rows, but we only have 2 generators. So it starts at the top and it says, can we meet the load without any generators? Because we have a battery and PV and battery. So first it tries to meet the load with that, and if it can, fine, it moves on to the next time step. If it can't, well, let's try row number 2. I just lost my screen. That's weird. Okay, so then, sorry. So it starts with the first row, and can I meet the load with just the first row? In this case, there's nothing's checked. So that means, can I meet the load without any of these generators? And diesel off, just relying on the PV battery. If I can't meet that load, I go to the next row. Can I meet it with the small generator? And if it can meet the load, fine. And it moves on to the next time step. But if that's not enough, then it goes to the third row. And in this case, can I meet it with the 1 megawatt generator? And then finally, well, if the load's big enough, maybe I need to use both generators. So you can set up this generator order in any way you want. If you have 6 or 7 generators, obviously you'd have a lot more rows here. So I did that, and just to show the results. So let me double click on this, and oh, I didn't mean to do that. Hold on a second. I meant to just start. So what it ended up saying, oh, well, actually, we can put in a lot of PV and a lot of batteries, and we have a very high renewable fraction. So I don't know why my screen seeps. Now I'm just looking at silver and a sun. I don't know what happened there. Okay, back to my screen here. Sorry, that kind of threw me. So what this says is that we need the 500 kilowatt generator for the 937 hours in the year where the 500 kilowatt generator is enough. And we only need the 1 megawatt generator for 24 hours out of the whole year. So because we have a lot of PV. If we found a system with a lot less PV, we go down here. I don't know why I keep losing my screen. Now I'm just looking at silver.
Yeah. No, we can see your screen now. You just don't see it. Just click on that part of the screen.
You can see my screen,
Okay.
but I can't see my screen. All right, there we go.
Yeah.
I don't know how that happens. Well, so let's I'll tell you what we'll do. We'll limit the size of the PV just to show what happens, and also to show you. Somebody asked this question: how do we limit the size of the PV? We could use the search space and just limit it, or in the optimizer, we can say the upper limit is really 1,000. And we can do the same thing with the batteries. We can limit the upper limit to 1,000.
Yeah.
And recalculate. The generator order runs much faster if you have many generators and you use any other dispatch strategy. Homer can run really slowly, but so the generator order is great for running much faster. So now, because I limited the size of the PV in the generator, the small generator is running 3,500 hours a year, and the large generator is running 72 hours a year. So it worked its way down that table, and actually for many hours of the year, it didn't need any generator because it had enough energy in the PV and the batteries. But then it worked its way down, and for 3,500 hours a year, it needed the small generator, and for 72 hours, it needed the large generator. And I doubt it needed both at the same time, but it might have. So we find that's really useful in two situations. One, if you have a lot of generators, it's more consistent, we find, with the way utility operators operate. They'll have a fixed schedule of under what load conditions do they use which generators or which combination of generators. So it's more consistent with that kind of operating strategy. And Homer runs is just a lot faster if you have many generators and you use the generator order. It's just a lot faster. So I did want to show that because I have the impression that many of the participants are utility operators with classic utility plants that have multiple generators, and so I thought it would be valuable to show that. Any questions?
Homer, Peter, would you like to show the part that you can schedule the genset operation?
Yeah, I'm looking at you and Hassan again. I don't
Okay.
how that
Because there could be participants that may have specific schedule which genset operates at what time. So
yeah.
yeah, you can.
So
No,
it's not. Oh, you're talking about scheduling them. I see.
Yes.
I misunderstood.
So you can click on the genset, and you can go to the advanced part, and yes, there.
Right. So you can.
So you can
So
force. Yeah.
Okay. Good point, Silver. I'm glad you brought that up. And that's different than what I was talking about. Here, you can simply force the generator on. So you click here, forced on, and you say, okay, which generator am I on here? I'm on the 500 kilowatt generator. So you say, no, we want this 500 kilowatt generator to run all night until 7 in the morning. And then maybe, at 11 o'clock at night, we can force it on. And then we could go to the large generator and say, here under schedule, we're going to force that on during the other hours.
The peak hours. Yes.
Yes, and that's what Homer will do. Um, I think it's better to let Homer optimize, but you might want to make 2 runs. Let Homer optimize the schedule, and because it'll vary. If you've got solar on the system, it's going to vary. On a sunny day, you're going to want a different schedule than on a cloudy day. So Homer will take that into consideration, but it could be useful to do that, and then also to do this thing that I just did of, okay, well, let's say we just ran the generators on a fixed schedule. It'll be more expensive and it'll use a lot more fuel, but it might be really useful and interesting to see how much more fuel, how much do you improve the economics and the operation of the system by being flexible and running the generators less on sunny days and more on cloudy days. So that can be a very interesting analysis to do. So we have that capability under the advanced capability here to do the
Yeah.
scheduling.
You can force it on, and you can also force it off.
Right.
Okay.
We can force it off during those hours. You have to be careful though, because if you force it off a lot, you might very well end up with an infeasible solution. You force it off during a period when, well, actually you really needed it that hour, you'll end up with an infeasible system. So you almost always do better by optimizing, but you might want to do this just to compare it to, you might have an operator that's insists upon operating on a schedule, and you can show them, well, here's why it's better not to do that.
Mm-hmm. Mm-hmm. Okay.
So then you can turn it off by hitting optimizer and just doing that. Okay, well, that's all I wanted to show. I thought it was really important just to show this generator order dispatch strategy. This one here. I thought I really wanted to show that.
We have a quick question. Can we address it? Right.
Sure. Yes.
This is from Dr. Tanveer. Over to you.
Hi, Peter and Silver. Just a quick question on the scheduling that we just discussed, and you just mentioned that Homer will give us the optimal solutions. But regarding the scheduling, I don't know what kind of optimization techniques is Homer using. But what I understand that let's suppose if we come up with another optimization technique and with another optimal scheduling, then we can compare that optimal scheduling with Homer. Is this correct? I mean,
right. So actually, there's 2 different optimizations going on. There's one within each time step. What generators to dispatch and whether or not to charge or discharge the battery. That's like an optimization happening in each time step. For clarity, I usually don't refer that as dispatch as optimization. I just call that dispatch, but it is a kind of optimization. But when we talk about optimization, like when we're showing this table here, and we call it the optimization results, that's optimizing the capacity of the different components. So it's a little confusing. There's 2 different optimizations going on. What you're talking about is, I think, is can we compare different dispatch strategies? So we do have these sort of canned, pre-programmed dispatch strategies. But we also have this one called a MATLAB link, and it's just a little too complicated to get into here. But you can create any dispatch strategy you want in MATLAB, and using the MATLAB link, Homer will run using your dispatch strategy. And I'm going to add it. I'm not going to be able to run it because I don't have a MATLAB program going. But if we did this now, if we hit run and we had a MATLAB program, on my computer ready to go, Homer would simulate both, and you'd see the results of the operation of the system, well, and also the design of the system, with both dispatch strategies or control strategies, and you could compare them, which one's better. So I believe that's what you were asking. I hope that's what that was. I answered your question.
Cheers, thank you. That is exactly what I asked from you.
Oh, great, good. I like that.
So Peter, we have another rather comment from Ejaz from Pakistan. Great learning experience for Homer in last 5 days. Since it is last day, I will appreciate if Peter could share Homer licensing details, including fees. More, I'm working as consultant on renewable projects, but not in industry. So I think this is more on a comment side. You can go on the website of Homer and then you can check out the licensing details and the fees. Right?
Yes.
Peter?
So on our, yeah, maybe I should just show on our website how to wait a minute, let me do something here, and I can just show you.
In the meantime, all participants are requested. So if you have any last questions, we can address those. Otherwise, we would be going on with closing this training session. If you have any questions, please feel free to ask them right now.
Am I showing my screen? Am I showing the Homer website here?
Yes.
Yeah. So if you go to our website, homerenergy.com, this is what it looks like, and here's the pricing information. We have discounts for academic users and students, and we have monthly licenses and annual licenses, and we have 3 packages. So the base package, the base Homer Pro package for standard, commercial use, is $500 a year, or $42 a month. And then there's upgraded ones, so I don't have time to go through all this, but there's different packages, or you can sort of have an a la carte, buy modules by the month. But there's a 21-day free trial. You have to register, which I'm not going to do right now because I have too many accounts. But so anyway, this is how you download it. The base package is $500 a year. And then there's upgraded packages with these different modules here, like the MATLAB link is costs a little extra, or these packages have multiple modules depending on which package you want. So there's a lot of flexibility here on the pricing. We also have concurrent licenses, so you can buy one license that many different people can use. If you have one seat, that means any number of people can use it, but only one person at a time. If you have 2 seats, then 2 people at a time. But then you can it's a shared license. You can share it with a lot of people, other people. So you can call it a shared license or network license or a concurrent license, all the same thing. So we have those as well. Just contact sales@homerenergy.com, or you can just buy this over the web with a credit card. Here. Sign in.
I think the participants can go on the website of Homer Energy and just check out the licensing fees and all the details over there. Yeah. And if they wish to have some trainings for their specific department, they can also contact the sales and marketing department.
Right, exactly. Yeah.
Okay, so last thing was, we have been asked multiple times by different participants that would it be possible to share the recordings of this 5 days training. So just for the information of the participant, this was a specific program activity of SAG Energy Center, and we have already we are in touch with the Homer Energy legal and the management over the possibility to share the recordings, and if we get the permission and everything is well settled, we would definitely post the recordings on our website. If not, still the content and the material concerning the presentations and the model exercises which we have done during these 5 days of training are available on our website for your checking out or for your reading at your leisure time. So with this, I think Silver, if you have no more comments, Peter, if you don't have any comments, so we should go on with the closing session.
Yeah, our goal is to make the recording available to the participants but we don't want them distributed beyond that, because this this is our job to do these trainings. But we're happy to share them with the participants, as long as they don't then pass them along to other people as well.
Well, normally what we do is we put it on our YouTube channel and share the link of that video on our website. So definitely we wouldn't be then able to restrict any other outsiders from
Yeah,
checking
but we might be able to help you with that.
Okay, perfect. We can sort out some password kind of an arrangement over there, maybe.
Right.
So let's Peter, Silver, do you have any last comments?
We have prepared the materials that you have distributed in your website. So I would encourage the participants to do the exercises. They can take advantage of the free 21-day trial of HOMER. So you'll have a feel of what HOMER modeling would look like. And that's a good starting point for them. So thank you for this opportunity to introduce HOMER to the participants.
Okay, so since we are over with the question answers and all the things, we have been. Yes. Nidhi, you want to make a comment?
Go ahead, Nidhi.
I'm sorry, I got late in turning on my webcam. There was some issue with the video.
No issue at all. Thank you very much for joining.
To introduce Nidhi, because she's she provides support, and she's in India, so she's in your time zone approximately. So she's your like local support person.
Nidhi, over to you.
So yeah, I'm here in India, and I just half an hour behind you. So always you're welcome to have any questions, and I would be there to help you with licensing, technical support, or like whatever I can do the best. So you're most welcome to have any questions, and I will reach out to you as soon as possible.
Well, actually, and Silver as well. He's not. Yeah. He's just a couple of time zones away.
Yeah, exactly. So that's the advantage of Silver and me in this time zone, because Peter has to wake up quite late.
And also related to the type of systems that you may be working in your region, we can relate to that with understanding of the region. Yes.
Okay, perfectly all right. So we will put contacts of Silver, Peter, and Nidhi on our website. So if any delegates wants to get in touch with them, they can obviously do so. So with this, we may go on to our final session. We have been okay. So we have some comments from the delegates. The Pakistan delegate Ejaz Siddiqui has said that it was a wonderful training for 5 days, and we have learned a lot during this HOMER training. And we are very thankful to the experts and the SARC Energy Center for arranging this valuable training. Then we have a comment from Mr. Geli Dorji from Bhutan. Thank you very much, all the resource person in SEC, for arranging this valuable training.
Our pleasure.
Now, thank you very much. So now we move on to our final session, which is the closing of training. We have with us, unfortunately, Dr. Nawaz Ahmad, who is the director of SARC Energy Center, could not have spare time to join us. He was quite busy in the ministry. So we have with us our program leader, Dr. Tanveer Ahmad, who will be giving the closing remarks. Over to Tanveer.
Thank you, Hassan. And first of all, I would like to thank Peter, Silver, and Nidhi, and on behalf of Director SEC. I wish we could be here, but it was outstanding. Being a researcher and an academician as well as a practitioner, it was outstanding to listen to you guys. Though I couldn't attend all the sessions in the 5 days, but whenever I was there, I learned something new, and I learned something useful, which could be done with HOMER. So definitely, I'm sure that the delegates and all other participants, they would have learned a lot from you, which was the basic purpose of this training. So thank you to all the trainings. I would also like to thank all the delegates, again, the participants, SN, our IT team, for conducting this training in a very professional manner. And that's it from me. I wish you all best of luck. Thank you.
Thank you.
Thank you.
Thank you, Dr. Tanveer. So final words. Thank you very much from my side to Dr. Peter, especially because of the odd timings at which he has to connect with us. Thank you very much. Thanks a lot to Silver and Nidhi for joining us and for giving this amazing training. We had learned a lot, all of us. And to the knowledge of all the participants, the contents are available on our website. You can go through it. And if you have any suggestions, any comments to make on this training, or if you have any suggestions for the future, for any future training you would like to have, you can post us through emails, and then we can arrange those kind of trainings for you. So thank you very much to all, and have a nice day. Bye-bye.
Bye.
Bye.
It's been a pleasure. I hope to meet some of you in person someday.
Yep.
Definitely.
Yes.
Hopefully. Okay, bye now.
Bye everyone, and stay safe.
We
Thank
have the
you.
new variant now, so please take care of yourself and have a healthy weekend. Enjoy.
Yes,
Thank you.
enjoy. Thank you.
Thank you. Bye now.
Okay, bye now.
Bye bye.